Good morning, everyone. Today we are going to talk about corrosion and degradation of materials. Um, we have learned on several basic fundamental materials, metal and metal alloys, composite, this polymer, ceramic, and composites. And then we talk about the corrosion. So the cost of corrosion, we know corrosion, right? Corrosion is a destructive electrochemical attack of a material, electrochemical attack of a material. For example, aluminum compounds shape, and there are several other. This is look at here, photos courtesy and Cindy National Lab used with permission. And so it cost 4 to 5% of the gross national product. So this is very, very high, 4 to 5%. In the US, this amounts to just over 400 billion per year. So it's a huge number. And you can imagine if we can just minimize, or this is which is impossible. If we can eliminate corrosion, we can save so much money. Electrochemical corrosion. So, for example, consider the corrosion of zinc in acid solution. Acid solution means that we have this hydrogen ion, this H plus. So two actions are necessary for the electrochemical corrosion. First one is a zinc, and these zinc atoms, and they become zinc ion, and also release 2 electrons. So this is so this one is zirconium ion. So zirconium, this is atom. Then the zinc, zinc atom and zinc the ion, and then have 2 electrons, free electrons. And then these free electrons will be captured by 2. This is a hydrogen ion. So then hydrogen ion will become this is H2, and H2 is the hydrogen molecule. And so the hydrogen molecule becomes a gas, and then this gas will be released. And you can see the zinc, and at the very beginning, the zinc atom is a solid, and then becomes the zinc ion, and zinc ion can be will go to the water, will go to the solution, right? So will dissolve in the solution. And you can see here, so this is zinc, this is a bulk zinc material. So you can see zinc atoms will become zinc ions. These zinc ions will go to this is acid, and the flow of the electrons in the metal and will be captured, as I said, will be captured by hydrogen, 2 hydrogen ions, then get 2 hydrogen atoms. 2 hydrogen atoms form 1 hydrogen molecule, and this which is a gas. So this is a reduction reaction. So this is oxidation reaction. This is acid solution. So other reduction reactions in solution with dissolved oxygen. For example, acidic is a solution. Oxygen, right? So this is oxygen gas. So the 4H. And also we have 4 free electrons. So these 3 guys, they will become 2 water molecules. So this is acidic solution. Also neutral or basic solution. So oxygen plus water and plus 4 free electrons, and we will have 4OH. So this is the base. So this is base OH. And so standard hydrogen electrode and 2 outcomes. This is corrosion. Okay, so this is dotted line means the corrosion here. You can see at the very beginning, we say this is the metal, and then as the time goes, and so this metal, these metal atoms become this is ions, and these ions dissolve in this solution. And then you can see this is a corrosion. So this bulk material becomes becomes less and less. So these are free electrons. These free electrons will go here and go to, this is water. This is acid. We have hydrogen ions. These hydrogen, as I said, hydrogen ions will capture free electrons to become hydrogen atoms. Then two hydrogen atoms will form one hydrogen molecule, and then the gas will be released, will go away. And so this is the metal in the anode. So this is a negative. This is metal in the anode, corrosion. So metal is if this metal is anode. Okay, so this is a standard electrode. This is a potential, a V metal standard electrode potential is less than 0 relative to the PT and this platinum. And so here, if this is the standard electrode potential is greater than 0, also relative to platinum. And so this now this time metal is a cathode. You can see here. So here, this is the platinum here. Okay, platinum. And this is platinum. So this is hydrogen. You can see, and these are hydrogen atoms. And these are two electrons. And this is gas. Okay, so this is gas. And then this is gas. And then this hydrogen gas will become one gas molecule and will become two atoms. The two atoms will release the electrons and become hydrogen ions. The hydrogen ions will dissolve in this solution. And then you can see these free electrons will go in the opposite direction from right to left. And then go here. Go here. Then we have electrons. So these electrons, the metal, these metal ions can capture these free electrons, then become atoms. The atoms will deposit on the surface. You can see here we can have more and more this surface. This is irregular surface because this is the deposition is kind of random, right? So that's the reason we have irregular surface on the on this deposition because of the deposition here. So you can see these two case scenarios, and if we compare the standard electrode, the potential. This case is for the metals that has negative standard electrode potential when compared with platinum. So this case is for the metals that have higher standard electrode potential when compared with platinum. Then this slide shows the standard hydrogen reference half cell. And you can see here, this voltmeter, this voltage. So this is a PT platinum electrode. And we have H a solution 1.0 mole. And then we just feed the hydrogen gas. You can see we feed the hydrogen gas at this is 1 atmosphere pressure. So this is a membrane here. This is a membrane. And then we talk about standard EMF series. For the different metals, they have different standard electrode potential. As I said, whether this is positive, the results, either this corrosion or deposition will occur is totally dependent upon the standard electrode potential. So this is one. As I said, minors means that, and they have the corrosion. This is corrosion, and they have lower standard electrode potential when compared with that of platinum. Positive means that this guy has higher standard electrode potential when compared with platinum. So metal with a smaller standard electrode potential occurs when we have two different metals. And for example, CD nickel the cell, because CD standard electrode potential of CD is less than that of nickel, and then so the CD close, nickel will have deposition here. So that means so this CD gives up free electrons, free electrons, and then the nickel electrode, nickel, this is ions, they capture the free electrons and then become the nickel, the atoms, then they have deposition here. So you can see this is one reduction of material, so this is addition of the material. Any questions regarding this slide? And then we show this corrosion in a grapefruit. So this is Cu cathode, as we have the Cu as a cathode. And so this is Zn as anode. And then these reduction reactions. So here is oxidation reactions. And so reduction reactions, we have these ions. When the ions capture the free electrons, they become the atoms. Then the atoms, they form these molecules and then get gas here. So here is a capture oxygen and hydrogen ions. They capture 4 free electrons, then become 2 water molecules. So this is Zn, and here is a corrosion. The Zn and atoms, they give up 2 free electrons and then become ion. So this Zn provides the free electrons. So this is a hydrogen ions here in acid. And effect of solution concentration and temperature. Also, we also use the example of CD nickel cell with standard 1 mole solution. And because we compare the standard electrode, the potential of these two guys, we know that Ni and has higher standard electrode potential than the CD. So we know that CD corrodes, and this is we have deposition on the surface of nickel. So this is a 25 degrees C. And if for this is a cell with non-standard solution, so this is a standard solution 1 mole, non-standard solution, we can see here. And so this Ni, CD, and we have no, this is 0 here, stands for standard. There's no 0, it's non-standard. So this equals, so this guy, but we need to end, this is a term. So this term, N, is the number of electrons per unit oxidation and reduction reaction. For example, for 2 here, okay, so 2 here. F here is a Faraday's constant, 96,500 and C mole, right? So this is C mole. And reduction, nickel minus VCD by reduce this one by increasing X, decreasing Y, and increasing temperature. And so you can see this is X, Y, decreasing X, Y, and increasing temperature. Then we talk about the galvanic series, the ranking of the reactivity of metals alloys in seawater, galvanic series. And so this material, they are more, they are inert, they are more cathodic. The cathodic means that they accept free electrons. Anodic means that they give up the free electrons. Then that means this guy close. And so here, and so this is the, and suppose we use the nickel here, and also you need nickel here, and this goes up and this goes down. So whenever you have the task, okay, to compare and to judge whether what will happen if you connect the two different materials, and you can come here and to look at this table and to determine which one is more cathodic and which one is more anodic. If this guy is more anodic, it is more active. That means this guy will corrode. And if this guy is more cathodic, that means this guy is inert, and this guy will you will see the deposit on the surface. So this is pretty much about this is the class for this corrosion and degradation